The goal of this talk is to convince you that quantum chemical calculations can and should be used routinely to support, question, or challenge structure assignments of natural products based on NMR spectroscopy. Natural products present an ideal target for quantum chemistry, as they involve relatively small molecules, maybe ranging in molecular weights to 1,000 atomic mass units, and involve relatively light elements. They present a serious challenge in that molecules are conformationally flexible. Experiment and calculation provide complementary information. The experiment provides an exact spectrum from which a structure may be guessed. I'm oversimplifying. Many spectra are used to provide that guess. The calculation starts with a known structure and produces a guess spectrum. The theory of NMR spectroscopy is fairly straightforward. The chemical shift is proportional to the difference in energies of nuclear spin states, which in turn depend on a property of the nucleus, the gyromagnetic ratio, and the magnitude of an applied magnetic field. The calculation is also straightforward with modern density functional models and is practical for molecules in the range of 600 to 800 atomic mass units. I'm going to use a two-part strategy. The first is we're going to establish confidence in the calculations by examining a collection of natural products for which either X-ray structures are available or which have been independently synthesized. We're going to then use that experience to evaluate the proposed experimental structures for a set of natural products which X-ray structures are not available. I'm going to use a single computational model, quantum chemical model. It is the Omega B97XD631G density functional model. This is going to be applied both for equilibrium geometry and for carbon chemical shifts. The Omega B97XD functional may be viewed as a significant improvement over the popular B3LYP functional introduced roughly 20 years before. Both of these functionals, the names, mean very little to those outside of the community. They're just names, and they really simply identify well-defined and well-assessed quantum chemical models. How well does this model do with the calculation of carbon shifts? Here are comparisons involving aliphatic and olefinic aromatic carbons for a set of maybe 100 molecules. They show an overall RMS error of about 5 parts per million, and they have both systematic and random components. This is not good enough. And we're going to apply to this model a set of empirical corrections. These are going to differentiate between carbon types and are going to account for directly bonded atoms in terms of power series in carbon X bond lengths. In total, the correction scheme involves about 50 parameters based on experimental C13 shifts for about 2,000 molecules, about 12,000 shifts. The corrected shifts show an RMS error of about 2 ppm, roughly 1/3 of those for the uncorrected shifts. The molecule strychnine, rigid, is a good example and a typical example. The shifts are typically roughly 1 ppm away from experimental values. There's some as large as 2, and there's some that are essentially identical. Next. Chemical shifts depend on conformation. Variations of roughly 2 to 3 ppm with subtle variations in conformation are quite common, and it's very easy to find larger variations. For example, between the trans and cis conformers of acrolein, you can see variations on the order of 6 ppm. Very few molecules are rigid, which means that you need to multiply the calculated chemical shifts for the individual conformers by their respective Boltzmann weights. The Boltzmann weight depends on the energy relative to the energy of the most stable conformer, as well as on the temperature. Boltzmann weights are more difficult to obtain accurately than other properties, and to do so requires sophisticated and fairly costly quantum chemical models. The only practical strategy is to employ a succession of models of increasing sophistication and cost, reducing the number of conformers that have to be considered as one moves through the sequence. The first step in any sequence has to be able to deal with 100 to 1,000 or even more conformers. The only practical strategy involves molecular mechanics, and the only goal is really not to miss any good conformers. It's the last step that's important to give you accurate Boltzmann weights. This needs to involve a fairly sophisticated model, and because of that, really needs to be applied only to a few conformers. The actual protocol used here has 5 steps. The first is MMFF, molecular mechanics. We throw away conformers that are higher than 40 above the best. The next step involves recalculation of geometries with a simple Hartree-Fock model. We throw away conformers that are greater than 40 again. The third step requires energy calculations with a simple density functional model, the same one used for the chemical shifts, and this allows us to discard conformers that are greater than 15 kilojoules per mole. The next and most expensive step requires geometry calculation with the same density functional model. And the final step involves energy calculation with a much more costly density functional model. You can see by these two examples the reduction in numbers of conformers. The first one is a relatively small reduction from 49 to 14 as one moves through the sequence. The second one is a larger reduction from 600 to 8 as one moves through the sequence. All of this can be fully automated. All that's required is an initial structure in any conformer, and what comes out is an average spectrum. There are two sources of errors. Errors in chemical shifts for the individual conformers, we already discussed that, and errors in Boltzmann weights. How good are the Boltzmann weights? There are no experimental data on molecules with several degrees of freedom. There are, however, very sophisticated calculations for a very few molecules, the most complicated of which is melatonin, with about 50 or 60 conformers. You can see here that the method used for the final step of the protocol matches the reference throughout the entire range. So we can have some confidence in that. Are these practical? Yes. Consumer-grade personal computers are quite able to calculate the NMR for flexible molecules in the range that we said we're interested in. Here are 3 examples of times. You'll see these are not instantaneous. The bottom line are total times. And a very tiny molecule will require 3 hours. A larger molecule, but not very flexible molecule, requires perhaps 7 hours. And a slightly larger molecule, but much more flexible, requires something like 60 hours. In all of these cases, the most costly step is the optimization of structure with the density functional model. What we're going to do now is to take this protocol, these two steps, Boltzmann average and chemical shift calculation, and apply it to about 700 natural products for which the structure is relatively confidently established because of an X-ray structure or because the molecule has been synthesized. The first thing to notice is that in only about half of these compounds is the conformation identified in the crystal the same or very similar to that identified by the calculations. This means that we can't count on the crystal structure to give us the best isolated molecule conformer, or in other words, crystal packing interactions are actually important. The distribution of errors in this set of 700 is rather tight. The overall error is about 1.8 ppm, similar to the error for the training set. The largest errors are on the order of only about 4 ppm. Most of the large errors are due to misassignments. I give a few examples here. This is of CH carbons and aromatic rings. I contend that's misassigned. More common are quaternary carbons, which are the hardest ones to assign. And here are two examples where I contend both of them are misassigned. Incorrect assignments are easy to spot because they necessarily occur in pairs. Okay, could we have done better? Probably not much. 1.8 ppm is close to the chemical shift variations noted among different solvents. We've observed that if we limit our data set to nonpolar solvents, we do slightly better than not worrying about whether it's polar or nonpolar. We've not done this. We've also not attempted to apply solvation corrections either to the chemical shifts or to the Boltzmann weights. Expectations. It's not unreasonable to expect that we should get a similar distribution of errors for natural products where there are no X-ray structures or synthesis proofs. More to the point, we should be able to challenge structures that show significantly larger deviations. The data are shown here. This is about 1,200 molecules. They're different molecules. The gray curve is that which is the result of the previous set. So this is the expectation set. I would divide these data into three categories. The green set are ones that fall inside of expectations. This does not mean that they're correct experimentally. It means that we really can't challenge them. The yellow set I would quote as questionable. They are too large, but they're not large enough that they might not be due to abnormally large solvent effects or to changes in conformation. Where they're restricted to a single center, they may be due to a change in stereochemistry. The red set is where I want to focus. They're the problematic ones. The errors are too large and often involve more than one center, often two or more centers. They're too large to be due to solvent effects or to conformation changes. They may be clerical errors. They may be mispeaks, or the structures may be wrong. An example of what I suspect is a clerical error is given by the structure on the left. The agreement between calculation and experiment is perfect. I've not shown it, with the exception of one carbon, which is off by 17 ppm. The molecule on the right from the same paper shows nearly perfect agreement, and in fact the offending center is now in perfect agreement. I would contend that it's a clerical error. Mispeak is probably this molecule, although this one is a little more complicated. The agreement is quite good, with the exception of one center, which is terrible. The bad center is in a very crowded region of the spectrum, so it's quite possible it's buried, it's been misassigned. And there appears to be a very weak peak in the experimental spectrum, exactly where the calculations suggest there should be a peak. All of the structures are not necessarily incorrect. They may be the wrong tautomer. This is a potential example of that, where the assigned structure is showing two very large deviations, whereas if I shift to an imine tautomer, the deviations are smaller. Some assignments have recently been revisited and revised. Here's one. The original paper, 2008, is clearly a problem case. The reassignment is much less so. Some molecules correspond to natural products that are different, that have previously been identified. The molecule on the left from 2007 is in fact Panacene from 1977. This is all confidence building. We can identify things that are clearly wrong, but what we can't do is to suggest what the correct solution is. Although in some cases we can take guesses. I'll give you two examples. The molecule on the left is in very good agreement with the exception of 3 carbons. 2 of them are marked. The third one is on an aromatic ring. If I simply provide a different and more stable isomer, the agreement is perfect. I would contend the structure on the left is wrong and the structure on the right is probably reasonable. Sometimes work from the same paper gives you the hint. The structure on the left is clearly wrong. There are several peaks that are too far off. I would suggest that it's either the structure on the right or something very close. The stereochemistry can be questioned. That's a nearly perfect agreement, and also similar to structures in the same paper. Summarizing, we've developed an effective and automated protocol for the calculation of Boltzmann weights. We've developed a reliable shift calculation method based on a simple density functional model. We can count on an overall accuracy of something like 2 ppm. We've used this combination to estimate errors in about 700 structurally well-established natural products. They're, with almost no exceptions, in acceptable agreement. And then we've applied this to about 1,200 natural products. And what we've found is that about 10% of them are problematic. The molecules, the 1,900 molecules that I've used here, are available with a web browser, the address given above. There are probably lots of errors in that. I would appreciate anyone pointing them out. You can contact me. I would also be perfectly willing and happy to discuss ones that I perhaps have challenged by their large errors, or molecules that you might be interested in. That's it.